representation learning to perform energy forecasting with applications to the operation of the smart grid. By milestone 2, I've completed the tasks of performing basic time series tasks, data preprocessing, feature extraction, covariance extraction, covariance input into the model, building deep learning models, and finding the mean squared error of the models. I've narrowed down my focus to the following papers. Some involve LSTMs, involving covariates, probabilistic time series, and scalable representation learning. Feature extraction involves the creation of new features, such as datetime features, which are extracted based on properties of timestamps, lag features, which are values at prior time steps that allow us to take a fixed amount of time and see what the forecast is in the k-flag, and window features, which rely on lag features and are a summary of values over a fixed window of prior time steps. Window features can include moving sum, moving average, moving variance, and more. One of the first tasks I performed was implementing a hierarchical time series framework. I implemented a top-down method, and top-down approaches involve first generating forecasts for the total series and then disaggregating these forecasts down the hierarchy. I've formed the summing matrix, which captures a proportion of contribution from each subseries weight to the total weight. I decided to implement LSTM models because LSTM is a good tool for data that takes the form of sequences. In theory, LSTMs can deal with an unlimited number of states. LSTMs work well over a wide range of parameters such as learning rate, input gate bias, and output gate bias. LSTMs are better than RNNs since RNNs have the vanishing gradient problem and short-term memory. I've implemented the vanilla LSTM, stacked LSTM, and bidirectional LSTM. Stacked LSTM is the same but with stack layers. A bidirectional LSTM can learn the input sequence both forwards and backwards. Covariates are an additional time series to help explain the primary time series. The process generating the covariates affects the process of generating the primary time series, but not the other way around. I mostly work with lag covariates, or features extracted from time series that is lagged by k periods. These covariates form separate columns in the data frame. From paper 1, there are a few ways to incorporate the covariates into the LSTM model. One way is to use the covariates as inputs to the first set of fully connected layers. A second way is to use the covariates internally by the LSTM gates as weights to the input for get, state change, and output gates. Lastly, combine them with the LSTM's output in the last fully connected layer. Here's a diagram that illustrates 1, 2, and 3. I've taken a main tool from paper 4, and it is the use of triplet losses that is adapted to time series to perform negative sampling. The intuition of triplet losses in the word-to-vec word representation learning model is to linearly separate pairs of context, comma word, and context, comma, random word, since the context of a word should be distant from the context of a random word. A triplet loss is a loss function where a baseline input is compared to a positive input and a negative input. In terms of time series, we want xref and xpos to be near each other because they're both subseries in the same series, and we want them to be distant from xneg, which is in another series. So I plan to incorporate the triplet loss given by this function into the Gluon TS custom framework for deep learning models. Gluon TS is a package for probabilistic time series forecasting, which includes generative models and discriminative models. I've implemented a feed-forward neural network and trained the model on my time series training data. Possible future directions include using the partial autocorrelation function to determine the lag number k, applying negative sampling and triplet loss to multiple subseries of synthetic time series to create linearly separable embeddings between different subseries, combining the hierarchical approach with generative models in the Gluon TS library. Some questions and challenges are how to incorporate hierarchical approach with deep learning model. Should I incorporate other tools such as dynamic time warping or Fourier transforms? How to capture properties of transseasonality in the representation? What sampling rules to use? Which LSTM to use? And finally, my future tasks include hyperparameter tuning, creating a GUI, finalized design of representation learning architecture, implementing my new ideas, and building a custom Gluon TS model by defining the training and prediction network and the new estimator.